Good day, everyone. My name is Jeremiah Aniebiet Okon of the Postgraduate Program in Environmental Engineering and Technology. I'll be your presenter for this seminar. I'll be presenting on the article Biological Wastewater Treatment and Bioreactor Design, a review, authored by C.M. Narayanan and Vikas Narayan in 2019. In this article, we'll be looking at the following: the introduction, the basics of biological effluents, key differences between aerobic and anaerobic processes, stirred tank bioreactors, membrane bioreactor, moving bed biofilm reactor technology, fluidized bed biofilm reactor, semi-fluidized and inverted fluidized biofilm reactors, packed bed biofilm reactor technology, downflow stationary fixed film reactor technology. Conclusion and references. To introduce the biological water treatment, it does plays a crucial role in environmental sustainability through pollutant removal, resource recovery, and renewable energy and bioproducts production. This system reduces the environmental impact of wastewater discharge, recover valuable resources, and supports green energy initiatives. Now, let's put this into context. According to the World Health Organization in 2023, about 2.4 billion people globally lack access to safe sanitation. And when we talk about safe sanitation, we don't just mean usage of toilets. We are talking about untreated wastewater, which contaminates our drinking water. This results in about 485,000 diarrhea deaths globally. And why this topic is necessary is because biological treatment bridges this gap as it directly addresses the United Nations Sustainable Development Goal 6, which is on clean water, and the Sustainable Development Goal 7, which is on affordable clean energy. How is this possible? Biological treatment removes up to 95% pollutants in our wastewater, making water reusable for irrigation. In some part of the world now, in some parts of Africa, even in the Americas, where drought is being experienced, biological treatment process, if it's being put into play, water are being reused and thereby achieving the United Nations Sustainable Development Goal, and also the goal on affordable clean energy. Because anaerobic digesters, as we'll see further when we go further, turns waste into biogas, and this is actually a renewable source of energy. There are actually some challenges to the biological treatment processes. We have we could encounter some challenges such as the operational costs, the performance and scalability, the product quality concerns, and also some regulatory hurdles, getting approvals and the rest from government agencies. Additionally, the efficiency of the biocatalyst may be affected by the waste composition and operational conditions. Now to the fundamentals of biological effluent treatment, the basics of biological effluent treatment. Biological effluent treatment uses beneficial bacteria and microbes to break down organic pollutants into simpler, harmless substances like the carbon dioxide, water, and sludge. So what it does in essence with the wastewater, it uses microbes to break down this into what harmless substances. And to achieve this, there are two key processes to this: the aerobic treatment and the anaerobic treatment. In further slides, we'll discuss more on that. But briefly, the aerobic treatment requires oxygen, while the anaerobic treatment do not require oxygen. The aerobic treatment breaks down the organics into carbon dioxide, water, and biomass, whereas the anaerobic treatment produces biogas, which is now efficient for our renewable energy. Differences between aerobic and anaerobic processes. Just like we already talked about, key differences are aerobic processes uses energy, oxygen, to break down waste quickly into carbon dioxide and water and sludge, whereas on the contrast, anaerobic doesn't use energy. It's slower but produces biogas, which is methane and carbon dioxide for energy, plus some sludge. In aerobic wastewater treatment, bacteria decompose organic pollutants with the aid of oxygen. This process reduces organic chemicals to simpler ones, ultimately producing carbon dioxide, water, and further microbial biomass. Oxygen is essential for the microbial activity that drives the decomposition of organic matter. Aerobic processes are typically more efficient in breaking down organic pollutants compared to anaerobic processes. Anaerobic biological treatment does not utilize oxygen during the decomposition process. The byproducts of anaerobic digestion include biogas, which contains carbon dioxide and methane. Sewage sludge is produced as a byproduct in both aerobic and anaerobic processes, reflecting the microbial leftovers. Now, while aerobic process primarily generates carbon dioxide and water, anaerobic processes focus on energy recovery through biogas production. A sample illustration is being made here. The beneficial bacteria, which is the aerobes in aerobic process, the beneficial bacteria, it's being fed with the contaminants and oxygen. Now it breaks this down into what? Water, our H2O, and into carbon dioxide and excess cell mass, which is the activated sludge. Whereas in anaerobic processes, it makes use of a beneficial bacteria called anaerobes. It's being fed with organic contaminants but no oxygen, and it breaks this down into carbon dioxide and methane, which is the beneficial component for energy source, beneficial energy source. Now, I want to further biological treatment method. We go on to the stirred tank bioreactors. This is an aerobic process also, and the concept of this is makes use of an agitated vessel. That's a large tank. Stirred tank bioreactors for aerobic treatment. It uses oxygen and agitation. The tank is being agitated to break down organic waste with activated sludge. And the process in this includes aeration, that oxygen is constantly being pumped in. After being pumped in, it's allowed to settle. After settling, it's being recycled. Then to maintain what? A continuous activity. It's a circular activity in this process. We have the mixing tank, we have the settling tank, and then we have the recycle line, which is this. This is the aeration process, the influent, the aeration process, and it's being pumped in. And after it settles down, the clean water is being discharged, while the sludge, the process repeats itself, and aeration continues, the process repeats itself. What are the challenges to this process? It's actually challenging because of the high energy cost, because it requires high capacity air compressors to make this process going. And approximately 60% of operational costs is linked to the aeration. Also, large tank volumes are needed for industrial loads to achieve this. But the benefit of this is that it balances oxygen demand and improves BOD COD removal, since it divides the influence into multiple injection points. So moving ahead, the next biological treatment method which we have is known as the membrane bioreactor technology. This is also called MBR. It's actually an advanced biological process in the sense that it combines the traditional biological treatment method and adds an additional layer, which is the filtration method, also using a membrane. How it works exactly is it combines the biological treatment with ultrafine membrane filtration to produce high quality treated water. It uses microbes, just like the traditional method, to break down waste like the activated sludge, and membranes to physically filter out even tiny particles, pathogens, and sludge. Ultrafine membranes, for instance, acts like a coffee filter. Like our coffee which we take, we use a filter to filter this and then get fine coffee extract. So this is what it does. This is the wastewater. This is the traditional process of aeration. It goes further. This is the membrane now, further to filter out even the tiniest particles and then discharges its pure contents. The next, moving on to the biofilm reactor technologies now, we have the moving bed biofilm reactor. This is the MBBR method. How this works is it acts like a biocarrier. It's small lightweight plastic pieces, often hollow cylinders. They swell in the tank, rotating in the tank, while bacteria grows on their surface, consuming the pollutants. Why this is beneficial? It produces actually a better cleaning method. Aeration tank is also needed. Air pumps keep carriers moving and supply oxygen for bacteria. Just like emphasized already, it uses flow-steam plastics coated with bacteria to break down wastewater pollutants. It's actually a compact and efficient, and then it can also be upgraded using either a membrane, and when this is done, it's the MBBMR because of the membrane here, or if it's not done traditionally, if it's just the MBBR process, a settling tank is being used in that case to separate the clean water from the carriers. So the next method is the fluidized bed biofilm reactor technology. This is an high efficiency biofilm treatment for industrial wastewater. How it works is the use of biocarriers, tiny media particles which are coated with biofilm are suspended in the reactor by upward flowing wastewater. Fluidization velocity is carefully controlled to keep carriers moving without washing them out. The key feature of this is biofilm aggregates are fully surrounded by wastewater, maximizing contact with pollutants. Also, this is advantageous in the sense that it allows uniform flow, preventing dead zones, like we have got in some fixed bed systems. It can handle large volumes of water due to efficient bacterial retention. It minimizes excess biomass generation also, and it's ideal for industrial plants with high organic loads. Albeit there are some constraints, some limitations to this, which are as follows. Constant aeration is needed to fluidize media. This will result in an high operational cost. Biofilm overgrowth can clog the system if the process continues repeatedly, less effective for nitrogen/phosphorus than hybrid system, and it's best for high-strength industrial wastewater like the food processing and pharmaceuticals. And here is an example of a fluidized bed bioreactor. An upward flow, like we pointed out, keep carriers constantly in motion. The next methods which we do have are the semi-fluidized and inverted fluidized bed biofilm reactors. Now, while the semi-fluidized bed reactor carries a hybrid design in the sense that it combines a fixed bed stability with fluidized bed efficiency. Now, the result of this, it's a partial fluidization which results in reduced aeration cost as compared to the fixed bed biofilm reactor. On the other hand, the inverted fluidized bed, which is the IFBBR, wastewater flows downwards. This expands the media upwards, and then this is best suited for fragile biofilms or sensitive microbes. The next which we do have is the packed bed biofilm reactor technology, the PBBR. How this works is the packed bed biofilm reactor technology uses stationary carrier media, just like plastic or ceramic pieces, coated with bacteria to treat wastewater as it flows through the system. Now, some advanced version actually combines this with ultrafiltration membranes for even cleaner results. In this technology, there are no moving parts, and as such, low energy is being used and simple maintenance is required. Simple to no maintenance is required. It also maintains the membrane technology and adds extra filtration also for a super clean water. Just as this, some of this illustration which we have here, some of the systems incorporate the membrane technology, and then it's equally also cost effective. Also, we do have the downflow stationary fixed film reactor technology called the DSFF. How this works is wastewater flows downward through a fixed bed of biofilm coated media like plastic, ceramic or rocks. Microorganisms on the media degrade organic pollutants as water passes through. What are the advantages of this? It's gravity fed, meaning no pumps is needed. Erosion, no pumps, no aeration needed. It's easy to construct and maintain, even distribution of wastewater over biofilm. Although there are some challenges to this, as the surface area must balance microbial growth, and there are also clogging risk to this. Also, material being used can affect biofilm adhesion and longevity, and it also struggles with sudden changes in wastewater strength. Now we can actually think of this just like a waterfall, whereby water falls through, passing through a bed of bacteria-coated rocks or plastic pieces. That's the downflow stationary fixed film now. Now as it passes through, the bacteria there grabs and breaks down the pollutants. Thereby that waterfall, there are no pumps needed, there are no bubbles needed, that's no aeration is actually needed. So it's a simple process, it's a super simple process to build and run. But it's actually works best with steady and predictable wastewater. It's best for rural areas now, small communities or factories with a constant waste stream. It's also an ideal for a small scale or decentralized system. Comparing the bioreactors so far we have talked about on this slide, the stir tank, it's simple but has limited capacity. It works for aerobic and also anaerobic processes. A trickle bed, it's low cost, it works for aerobic only, slow flow rates, while the MBBR, the moving bed biofilm, it's high efficiency but is sensitive to agitation. The fluidized bed, it's high capacity and conversion, particle loss risk. The semi-fluidized, better conversion than the fluidized, but higher cost. The inverse fluidized, low cost, larger particles, lower capacity. While the downflow DSFF, simple, low cost, anaerobic, only large space is needed. So here is a bioreactor selection guide which will aid us in selecting a suitable treatment method for our processes. For instance, if this is the wastewater now, if this is the wastewater, we just have to ask ourselves some certain questions and then we determine the best possible process to take. If it's just for pilot testing, then simple stir tanks can suffice. They are simple and then they are also adaptable. Whereas if it's for an industrial scale, if an aerobic process, a semi-fluidized bed can also suffice. If not, a USB or anaerobic MBBR, that's moving bed, can suffice. Whereas if the wastewater has high organic strength, if that's the case, if it needs biogas production, a USB reactor can equally come into play, which is highly efficient for strong waste and produces methane. If not, a fluidized bed can come into play, which is compact, has a compact design and high treatment rate. If it's a wastewater with high organic strength, but no low/medium strength. If that's the case, if there's any constraints in budget, in finances, then the trickle bed can come into play, but if not, the MBBR can also come into play. So in conclusion, the various biological treatment systems which we've just discussed, we have seen that they can clean water sustainably. As a matter of fact, they can go a long way in purifying wastewater about 95% of the time. And then all methods, both the sludge, the biofilm, the reactors, they either face energy or efficiency or cost balances. And we also have seen that smarter designs and hybrid methods, they are cheaper and then it also produces greener treatment. Then we could also see from this that no one size fits all in the fact that we actually need to match the technology to the specific waste stream. We can't use a particular technology, for instance, like the membrane technology for all the waste streams, maybe in a domestically, industrially, different plants, so no one size fits all. References to this article, the article that we are cited are given here, this by and Narayanan CM, and the second by Ogunwumi Oti Adeniyi on the book Wastewater Treatment and Sludge Management Systems, the gutter to good approaches. Thank you very much for your time. I remain Jeremiah. I'll give the room for questions or contributions. Meanwhile, if time do not permit, I could also be reached through this email ID here for any further comments or contributions. Thank you once more, everyone.